Konstantinos Salonitis. Professor Salonitis is the head of Sustainable Manufacturing System Center and the Deputy Directors of Manufacturing Theme at Cranfield. He sits in the steering committee at the UK Jiangsu 2020 World Class University Consortium. He led the development of the Sino-UK program on aerospace manufacturing with Nanjing University of Aeronautics and Astronautics, NUAA. He's a visiting professor at both NUAA and Jiangsu University. His research is in the area of sustainable manufacturing, modeling and simulation of manufacturing processes, and system and lean and green management of manufacturing. Professor Salonitis is leading the Sustainable Manufacturing System Center at Cranfield University, SMSC. In SMSC, fundamental science and thought leadership on the technological, economic, and social context apply to identify ways forward for commercial success and sustainability. Activities are tailored to the center's industry partner needs and include applied research, technological transfer, teaching, consultancy, and short courses. Professor Salonitis has published more than 250 research papers in major international journals and internationally referred conferences and authored 4 books. He's a chartered engineer, a fellow of Institute of Mechanical Engineering, and a member of Technical Chamber of Greece. He's also a fellow of the Higher Education Academy. So let's welcome Professor Salonitis.
Thank you. Thank you. I'm going to remove that mask, otherwise I won't be able to see anything after a while. Thank you very much. Let's go to the next slide, please. And probably we can skip this one as well. So I'm going to start with a very short introduction to the center, Sustainable Manufacturing Systems Center at Cranfield. This is a £4 million turnaround per year center. It is composed of 7 academics. We've got something like 35 PhD students and more than 150 MSc students, because Cranfield University is a postgraduate only university. We don't have any undergrads. And previous one, please. And as you can see from the word cloud, we are dealing with all the things that are relevant to what we are discussing here today. We're dealing with things like sustainability, net zero agenda, circular economy, green manufacturing. We are also using quite a lot enabling technologies like Industry 4.0, like lean manufacturing, in order to make things greener, smarter, and cleaner, as we say. And by cleaner, and I have put the C into parentheses, is that we're also trying to look how lean manufacturing, lean management can help make things cleaner without having to rely too much into capital expenditure. So sometimes the easiest things to be done are the cheapest ones, and actually we can get quite a lot out of this. Next slide, please. So we've got a number of different areas of research, as you can see from the slides, and the different colors. We're developing and we're improving existing manufacturing processes. Actually, what I will be discussing today is on casting, foundries, and how we can make things a little bit more cleaner and greener there. We are also playing a lot with circular economy ideas. We are helping a lot of companies to transition to net zero factors of the future. We're developing new materials. As an example, at the right side of the slide, we are developing bulk metallic glasses, which are basically metals that are amorphous in terms of their structure and can have specific properties that can make things a little bit greener. We are also using Industry 4.0 and everything that comes along, so sensors, Internet of Things, big data analytics, in order to help make things greener. And actually, one interesting point of research that we do in this area is trying to figure out how much consumption, how much carbon footprint comes with data. So whenever we are using data, there is an embodied energy, and we need to find out how much of this energy actually is consumed during the use of this data, and assess whether it makes sense actually to collect data or not. And last but not least, we're looking also on how to make changes in the management side of things, so in terms of how to optimize the operations. Okay, next slide, please. Just a couple of examples of what we do. We're using a lot of simulation technologies, depending on the type of the problem that we're trying to solve. So all the way from material and what is going on at micro level to looking to what is going on in the case of manufacturing processes. So a couple of examples here is at the top, it's simulation of a grinding process. Then there is a simulation of additive manufacturing and also simulation of casting, all the way to what is going on at the systems level, looking at the supply chain, looking at the impact that we might have when we are dealing, for example, with specific soft aspect changes in the system, like, for example, what would happen if we increase our investment in teaching, in training, and so on. Next slide, please. So, to set the scene, there is a lot of discussion about net zero agenda, which basically means that what we are trying to do is somehow offset every kilo of CO2 emissions with another way of capturing these CO2 emissions, either through carbon capture and storage technologies. But these technologies, very promising, but not mature enough to be deployed at full scale. So in order to make it happen by the 2050, we need to somehow squeeze this red bar as much as possible so that we make life and technology easier for carbon capture and storage. And what we are trying to do, at least within my center and with the projects that we are running, is squeeze that red bar as much as possible so that then we can, if possible, reach the absolute zero. Next slide, please. And on that basis, quite a number of years ago, we had quite significant funding from EPSRC, EPSRC being one of the research councils within the UK. And the idea was to use the small is beautiful approach. So instead of looking at bigger, instead of looking at economies of scale, look at how we can actually use as much as needed and not more than that. And when it comes to casting, next slide, please. This is the thing that we usually see when we, or usually what we imagine as casting being a process that requires a material, in this case metal, to be melted, which means that it requires a lot of energy to go into the process. Then, in most of the cases, we melt more material than we need, so we keep that molten material for quite some time, so there is some holding time, and that holding time again requires quite a lot of energy, till the time that we actually pour the metal to a mold, to a die, and let it solidify, and at the end have a final product, which again, we'll probably need some post-processing, which means that we will have to remove some of the excess material, which might end up being recycled at the end. Next slide, please. So this is quite an energy-intensive process, and just by being so energy-intensive process, it's quite important for us to focus to that process. As part of this small is beautiful set of projects, we had the chance to discuss with a lot of foundries to give you an idea of the scale. Foundries in the there are about 600 to 800 foundries in the UK. In China, there are 20 to 30,000 foundries. So the scale of operations is huge. And all of these foundries are using quite traditional processes. Foundries, and basically the people who are working within foundries, they believe, and probably they are right, that casting is the oldest process mastered by human beings. And being that old, that traditional, it's very difficult to change their mindset, to change their ways of doing things. And on that basis, we had to find ways of communicating with them to help them understand what is the impact or what might be the benefit if they were to become a little bit more sustainable. So starting with visiting a number of foundries, we collected data as such as, for example, energy consumption and production. And that is the type of level of granularity that foundries are going into. They only know, for example, how much energy they consumed over a period of a month, let's say, and that is coming out of their energy bills. And for that specific period of time, they know how much they produced. And then they can, in a way, identify whether there were any specific changes, whether there were deviations from the average, and that's the best that they can do. But this sort of information cannot give us a lot of insight about whether there are specific process steps that might have to be improved, whether there are areas where we should make some intervention, whether there are specific areas, like if we do a Pareto analysis, where we can see where we could have the maximum benefit. So next slide, please. And on that basis, we developed an energy audit framework that was published a few years ago at the Journal of Clean Production. And we used that audit framework to actually go into a foundry, collect data in different settings, from different process steps, in order for us to be able to then identify the area where it would make more sense to go and invest, to go and do some changes. Next slide, please. We also worked a lot on the visualization of this data. So we used different visualization techniques. We used IDEF0, for example, which we then could actually dive more deep into the IDEF0 to find out exactly what is the sort of input, what's sort of the output of specific processes. Looking also at waste, but then again, we try to get away from the whole notion of waste and consider that as byproducts, because it might be a waste for one specific process, but it might be input, it might be raw material for another process. And there is reason for us to actually try to find out whether there is some residual value in that sort of waste as a byproduct. And also we use Sankey diagrams. I think in the last 4 or 5 presentations, we've seen a number of different Sankey diagrams. We used quite a lot of simulation as well. This was also published a few years ago at the Journal of Clean Production. Depending on what sort of problem we are trying to solve, we were using different levels of simulation. So, for example, using molecular dynamics, we were able to figure out what is the optimum cooling rate in order to solidify the material. In this case, this is pure aluminum, or high purity aluminum at least. So that we could find the best cooling rate and actually what is the overheating temperature that we should go to in order to minimize the energy efficiency, but at the same time without having an impact on the quality of the final material. So without having, for example, any vicinities which were capturing air or whatever. In a similar way, we can look at the casting system itself, so the design of the mold, the design of the die, so that we can actually minimize the material that needs to be recycled afterwards. So instead of using, for example, conventional gravity casting, by using counter-gravity casting, the material that needs to be recycled then is minimized. And again, the idea was to somehow assess, both from economic but also from quality point of view and energy efficiency point of view, the output of the process. Next slide, please. At the same time, and this is another paper that published a couple of years ago, we looked into the dematerialization and the impact of using different materials for the same type of product. So if we look, for example, here, the cylinder head of the automotive, of a car engine, which is the single heaviest component in a car, we can use either a gray cast iron or aluminum alloy. And in the case of gray cast iron, because the material is stronger, the size of the engine is smaller, but nevertheless, it's heavier. And there is a lot of discussion about lightweighting vehicles. If you lightweight a vehicle, then you end up having less emissions during its lifetime, during its use. However, if you invest in actually using aluminum, you are spending quite a lot of energy to start with in the manufacturing phase. And you have to actually open up the boundaries in order to see exactly where the sweet spot is. So this initial energy that we need to spend for actually having the aluminum needs to be offset by using the car for longer. Otherwise, you will never get back, you will never get the return on your initial energy investment. And we found out by comparing 4 different aluminum casting processes, so low pressure, high pressure die casting, and so on, that we would have to run a vehicle of the same size with the same performance for somewhere between 170 and 230,000 kilometers in order to start paying back for the initial energy, which is actually quite a lot by the way we use cars nowadays. Next slide, please. We also looked at coming up with decision-making tools for helping foundries. Because, of course, energy is one thing. And as I said at the beginning of the presentation, that's not so easy to get across to the foundries. There is also the element of quality, time, and so on. So we use different multiple criteria decision-making techniques. And the problem with this sort of techniques is that because there are different stakeholders involved in the discussion, you might actually weight the different criteria with different weight factors. So how do you come up with a structured way in order to be able to compare and get some sort of decision made based on data without relying on this subjectivity of the one who is actually weighting the factors? That was published earlier this year at Journal of Clinical Production, where we developed an automatic way of weighting the factors and help with increasing the objectivity of the results. Bring everything together as part of this project, we try to look at developing a framework, a toolbox that Foundries, and not only Foundries, now I'm working with a number of aerospace manufacturers in order to adapt this framework to their needs as well, where we try to see basically how we can help them decide what is the best approach when it comes to energy efficiency. So what are the criteria that they need to select? What are the sort of data they need to capture? How to actually use this data in order to end up being able to assess which, for example, supplier is better than others in terms of coming up with a greener product. That small is beautiful led to a new project. This is called the Transfire Hub. It started this July. It's funded from the UKRI. It's part of the Industrial Strategy Challenge Fund. It is a hub with 12 research organizations, 20 COIs in total, which makes it a challenge. We've got 50 companies that are supporting the project. It's a £5 million funding with another £5 million coming from the companies as a matching fund. And what we will try to do is look at the different foundation industries. Within UK, foundation industries are responsible for 75% of the material produced every year. And they are also responsible for about 10% of the carbon footprint of the country. So we will try to work with these foundation industries in order to find out how they can become more competitive, how can they become more energy efficient, how can they actually meet the net zero agenda, and at the same time, how can they work with the local communities that they are based? Because this is something that has not been taught a lot over the years. The project is led by Cranfield. I am the deputy director of that project, of that hub, and there are, in the project, there are co-Is from universities like Cambridge, Exeter, Leeds, York, the list goes on, and I cannot remember all the names. So if you move on, please. So the idea is moving from this sort of approach where we basically have input, output, and waste. We want to capture as much as possible the different waste streams. We want to use modeling. Next, please. So we have 3 work streams. The first one is about identifying common processes within the different foundation sectors, finding out good practices and trying to figure out whether we can use these good practices. Also using modeling, also using Zentani. Zentani is something that's coming from lean terminology, something that Toyota came up with. It's basically the minimum energy required to achieve a process from physics point of view, and this can be used as a benchmark. Next one, please. Then there is work stream 2, where basically we're looking at the byproducts. So we forget the word waste, we're looking into the byproducts. How can we use these byproducts between the foundation industries? So maybe a waste for one of the foundation industries might be a raw material for another one. And then the third work stream is on working with communities. So for example, capturing low-grade heat and using that for heating local communities, houses, and so on. And eventually what we want to do is, instead of having traditional black factories, again, this is black again, but instead of having this linear approach, having a more circular approach and working with the communities at the same time. I think that was the last slide. Thank you very much for your attention.